The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to today's webinar entitled IEC 61508, Second Edition, Get Educated, Get Compliant. Today's event is sponsored by UL and produced by WebAttract, your end-to-end solution provider for informational webinars. I'm Lori Dearman, and I'll be your moderator and one of your hosts for today's session. In just a few moments, we'll be reviewing the agenda, but in a nutshell, today's focus is about hearing from some distinguished UL subject matter experts as they review 5 new improvements introduced in the second edition of IEC 61508. And of course, we'll be taking your questions during the Ask the Experts segment at the end of the discussion. Our goal today in delivering this webinar is to provide each of you with information which we hope will allow you to plan, strategize, and capitalize on the requirements, and be better prepared to design products that meet the new requirements and integrate the product into systems. But for now, let's get started, as we do have a lot to cover. Well, we've invited you, along with over 400 professionals from 6 countries and 27 states and provinces, representing industries such as OEM, controls manufacturers, systems integrators, AHJs, government regulatory, and others. All of you to learn about the important changes to the standards and the impact that they have on component manufacturers that result in higher degree of confidence for manufacturers, integrators, and end users alike. Now, regardless of your industry segment or location, we're confident that you'll find today's webinar of value. Now, speaking of feedback, we are here to talk about the notable changes in the second edition of IE 61508, but to get into the discussion, how about we do a quick poll to get a sense of where all of you are in terms of your familiarity with the second edition. So coming up on your screen right now is the first of our polls today, and that is, what is your level of familiarity with the second edition? We'd like to hear from all of you. We'll go ahead and take a look at how that came out. Well, looks like the majority of us, 77%, have weighed in as not familiar. About 22% come in as somewhat familiar, and 1% very familiar. So that's about what we were expecting, and I think there'll be something for everyone on today's webinar. So with that, I would like to go ahead and bring on our first speaker, Kevin Conley. Okay, now, Kevin Conley has 20 years safety certification experience. He began his career certifying that products such as relay, PLCs, motor drives, and circuit breakers meet the requirements. Kevin has helped establish UL's presence overseas by developing industrial control and power distribution business in UL European offices while living in Germany for 3 years. Kevin is the business manager for North American power and controls business and also initiates new business lines such as the elevator, ACO, business, and functional safety. Kevin has a BSEE and an MBA. And Kevin, it is a pleasure to have you here today. How are you?
I'm doing great, and I get to talk about one of my most favorite subjects, so how could it be better?
All right. Now, before we dive into a more detailed description of the changes, Kevin, can you talk to us about the impact of the changes in a broader sense and why these changes are important for all of us to know about?
Sure, Lori, I'd be happy to. So first, why are these changes important, and who are they important to? Changes are important because they provide benefits to every link in the supply chain. So we start at the supply chain all the way at the component level of sensors, ICs, or even software. We now have a more formal methodology for evaluating the functional safety of these devices in accordance with 61508. So we'll show how this will benefit the component manufacturers by giving them the ability to declare compliance, and how this benefits their customers as they have the confidence the components will meet their needs. At the subsystem level, there are now more internal process requirements that require transparency. What this will do is help the manufacturer manage the product lifecycle better. Later on in the product lifecycle, with these requirements, manufacturers now can more easily see whether any revisions to the design affect the functional safety of the device, and then easily see whether they need to revisit the safety case. The benefits of the ASIC and FPGA are making ASIC and FPGA more prevalent. Manufacturers, however, up until now have had difficulty with using these devices in a functionally safe design. Now, with the new requirements, there is a formal methodology for evaluating an ASIC and an FPGA system. So all of these changes are going to clarify requirements and formalize requirements so that the end user now has a higher level of confidence when they have a system completely designed to the 61508 second edition.
Well, thank you, Kevin, for helping us to set the stage on why these changes are so important for us to learn about. But don't go too far, as we'll be calling you back after Thomas walks us through some of the more details around the changes. All right?
Okay.
Okay, so here's a bit about Thomas in the way of an introduction. Now, Thomas Mayer is UL's principal engineer for the newly established Functional Safety Certification Program. He has 18 years of experience in the field of system safety and functional safety applied to various domains such as avionics, onboard automotive, automation, and process industry. He is an active member in standard working groups for IEC 61508 and IEC 61800-5-2. Thomas has a doctoral degree in engineering from the University of Stuttgart. Thomas, welcome to the webinar. You're joining us from Denmark today, is that right?
That's correct. Thank you, Lori.
Yes. Well, Thomas, on the screen we have a brief agenda of what you'll cover today, but I think you've summed up the thrust of the changes in the second edition quite succinctly on the next slide. So could you share that with our audience today?
Of course. Thank you. Well, to start with, I want to say, well, the principal aspects of functional safety, the principal concepts of functional safety as defined in IEC 61508 have not changed. So you still will have to look into redundancy, you will still have to look into random hardware failures and systematic failures. So maybe if you're meeting the standard for the first time, you will maybe not agree that these changes, they are radical or revolutionary. However, for those of us who have worked with the standard for some time, or we know it well, I think really these changes, they are remarkable. And in summary, you can say that all these changes, they are changes to the better, because they reflect and formalize how the standard, the first version of the standard, pretty much has been used all the time, in particular to certify subsystems and components. And there are also a couple of loose ends and weakly defined requirements, and the standard has gotten stronger and more formal about that. So in the end of the day, as a summary, you can say really a change that provides more safety.
Well, thank you, Thomas. And now we'll discuss each of the 5 changes in a bit more detail. So the first one on our list is increased focus on traceability. Can you explain this change and also give some examples of the impact of the change on manufacturers?
Yes, I'll do so. And it's maybe not by chance that we choose this one as the first one, because this is really where we think that an improvement of safety has been achieved by an increased focus on traceability. Traceability has been a requirement already in the first edition, so from a formal perspective, it's not really a change, but as we say, it is an increased focus, and that particularly comes true if you look at the software part, at the part 3 of the standard in the second edition. Here you will see the word traceability literally all over the place. I try to visualize that a bit by using some colorful arrows, blue arrows and red arrows, and there are 2 types of traceability. That's my own definition. You won't find that definition in the standard, but there's a vertical one indicated by the blue arrows that pretty much reflects the relationship of refinement and implementation that you will follow in a development project. And then there's the horizontal dimension of the traceability, which pretty much reflects the validation and verification relationship between the artifacts that you create during the development. And that's, as we will see, it will be very helpful to come up with a good safety argumentation, of building a good safety case. And how such a safety case can be constructed and will be helped by traceability. I try to visualize this, get this maybe a bit overloaded slide here, but this is first of all to show that traceability is traceability between artifacts, between pieces of information, basically, that you will create in a development project. So this slide is divided in 3 columns, you could say. There's one, the analysis, that's where you really identify what safety is about. That's where you do your hazards and risk analysis. That's where you do your failure analysis, where you find out what can go wrong. And all these things, they must be completely addressed by your system, by the system that you design and develop. And then you need to verify that you have addressed all these things completely and correctly. So the horizontal traceability between artifacts will support your argumentation in constructing that dimension of the safety case. And at the same time, you still have the vertical dimension, the blue arrows, which will tell you that a safety requirement that you have defined, that you have refined it completely, that you have implemented it completely, and that will allow you to really make sure everything has been considered, everything has been verified down to every single hardware component and every single line of code. Another important aspect of thorough traceability is its support in change management. Change management is particularly challenging for the systems 61508 is looking at, because these are software-based systems, and software-based systems are complex, very easily get complex, and software-based systems are relatively easy to change. Just change a line of code and that bug is fixed, or that additional feature required by the customer is there. And, but you need to make sure that safety is maintained, and you need to make sure that by doing impact analysis. If you have a certain change in a requirement, what does it mean? Where are the impacts? What are the effects of it? And having traceability will allow you to clearly identify all the impacts, again, down to every detail that is needed, to every hardware component and every line of code.
So our next change to discuss is the concept of elements and compliant items. And maybe you could walk us through that, so and point out anything that we should pay particular attention to.
Of course, and I think also these are quite important new concepts in order to explain a bit what an element is. Again, a slide that is a bit busy maybe, but I try to use some color again to make it a bit more understandable. But what I use here, the black lines, they represent, they're copied from the standard, and this is a diagram, a block diagram of a safety-related control system as it is the scope of IEC 61508. And such a safety-related control system consists of subsystems. And subsystems, they are very roughly defined as the input subsystem. Then you have, that can be a light curtain, for example, or simply an emergency stop button. You will have then a subsystem that processes it, the safety-related logic, and you have some output devices, the actuators, that really connect again to the physical world and create a safe state. And you could have some safety-related data communication, safety-related field bus, and so on. So these are the subsystems, and subsystems, they can, of course, further be decomposed. And this is where we have the elements. And an element, that can be a single contact, that can be a single contactor as an output, that can be a single encoder in the input, that can be a single microprocessor in a safety PLC. And subsystem and element, somehow they, of course, existed all the time, also in the first edition. But it's only here in the second edition that subsystem and element are really defined. So you find definitions in the part 4 of the second edition of IEC 61508.
And can you further define for us the concept of compliant items?
Yes, I think before I do that, it's important to understand also that the concept of element is not only defined, but you can say the second edition is pretty much built around this new, or this now better defined element concept. You will see that a number of safety or functional safety parameters like safe failure fraction, they are now defined as element properties, whereas they had been defined as subsystem properties in the first edition. Systematic capability, that's an element property too. So you start building your system really by looking at the elements, try to give you the needed systematic capability, the needed safe failure fraction, and then you combine elements to build the subsystem. Combine elements in series to build channel, you combine them to parallel to build redundant channels or to build diagnostic channels. And elements, they can comprise hardware only. Very obviously can consist of hardware and software. That would be the case for a microprocessor. And what is very interesting, they can be software only. Elements can consist and be built of elements. You can have a sub-hierarchy in the elements. And what is really important, this brings us to the second part of that section, is that elements can be what the standard defines as compliant items.
So now might be a good time for you to define for us the concept of compliant items.
Now it's a really good time to do that.
Oh, right.
And because this compliant item means that you can, every item within the system hierarchy, as it is defined in IEC 61508, and as I have tried to visualize it on the previous slide, can be a compliant item. So this means you really have a formal framework now to do pure software component certification, like safety-related real-time operating systems or safety-related communication protocol stack. This is the framework to really certify functional safety certification of microcontrollers, of ASICs, FPGAs. Now, if you're a functional safety engineer, you will say, well, functional safety is not only about software, it's always software and hardware. How can you certify software only? Now, the answer to this is the compliant item safety manual. Standard has two annexes in its parts 2 and 3 that define the requirements for the manual that you have to provide with a compliant item, with a compliant element. And you have requirements in part 2, which is about the system and the hardware, and you have requirements in part 3, which is about software. And in any case, even if you're only developing a pure software component that is supposed to be a compliant item, you always have to both fulfill requirements from part 2, which makes reference to the hardware platform where the software needs to be integrated, and part 3 is then only the additional aspects that would be relevant for software.
Okay, I believe that wraps it up on elements and compliant items. So shall we move on to redundant channels in a single integrated circuit? This one here, I would call the first things we looked at. They were really clarifications or increased focus, whereas what we're looking at right now, that's really an enhancement, I would say. And this is requirements about safety-related, about how to build a safety-related subsystem on a single processor, on a single integrated circuit. And this reflects, well, the trend, the well-known trend. There are multi-core processors, FPGAs are increasingly used by component manufacturers. And of course, the natural question is, why wouldn't a multi-core system on a chip not implement also multiple safety-related channels, or one safety-related channel and a diagnostic channel, and that together on the same chip as the normal non-safety-related application? But such on-chip redundancy was not possible, was not allowed until now. You always had to consider this as one physical channel. It always had to be a 1 out of 1. You could not argue for a 1 out of 2 structure. And for obvious reasons, because there's, of course, electrical coupling which you need to expect there. There can be shorts, there can be crosstalk between redundant signals, and also temperature will become a common cause for a failure that both channels fail at the same time because it's so close. Normally, the argumentation is temperature is not that much a problem, because if the two channels, they are physically away from each other, then because temperature is a slow phenomenon, they will not affect both channels at the same time.
But this, of course, changes if you have such a high integration of the two safety channels. And the part 2 of 6.15.08 second edition has a formal annex, Annex E, where really the it's called the architectural requirements are stated that allow you to claim redundancy on a single chip. And it's called architectural requirements. I think there are quite a few architectural requirements, but I think it also contains layout requirements, and it contains some limitations. So I will use that classification to tell you a little bit more in detail about these requirements. So really, architectural requirements, quite obviously, what you need to do is to separate physical blocks and substrate for each channel, and that includes each monitoring element, such as watchdogs. So there must be clear separation. If you have diagnostic elements, a diagnostic channel for both safety channels, so if you only have one, then there is also a diagnostic requirement, a diagnostic coverage requirement for a diagnostic channel. It's quite interesting. And you must, of course, make sure that that separation is kept throughout the design. Each channel must have its own separated inputs and outputs. This should not be only the functional I/Os. You can also take care that the same is true for example, clocks and power supply. There's a minimum diagnostic coverage per channel of 60%. And as I've mentioned before, temperature is a critical aspect. So there's a requirement, there must be temperature detection. The only possibility to get away from that is if you have a really high diagnostic coverage, more than 99% for each channel with all the other diagnostic means. But that is typically normally hard to achieve. The limitations, well, it's limited to SIL3, so you can maximally build a SIL3 subsystem. The concept of element synthesis, which means that you, if you have two independent channels, that you are allowed to have a lower systematic capability, and by combining you get a systematic capability of the next safety integrity level. This is not possible. So if you do a SIL3 system on a chip, you always must also fulfill the SIL3 fault avoidance requirements. And then there are the layout requirements. So really the separation of channels is then achieved by well, obviously increased distance, or maybe even better through isolation by using potential rings between these two blocks. And well, you must make sure this is valid for the complete channel, so you need to have separated inputs and outputs, no routing through another block, and so on.
Now, we've looked at the hardware requirements for on-chip redundancy, but are there any particular requirements for the development process of such chips, which I believe takes us to the topic of FPGAs?
This is correct. Yeah. Well, FPGAs or ASICs, well, I think we put FPGAs here because I think many component manufacturers are looking into FPGA development. Really, the question is this software or hardware? So clearly, it is something in hardware, so you could claim, well, 6.15.08-2 in its own form applies. But 6.15.08 second edition recognizes that there is really a similarity between complex hardware development and software development. In both cases, well, it is the complexity that is the enemy, if you want, and you need to apply measures of fault avoidance. And I think the most fundamental measure of fault avoidance is a good process, is the V-model approach. So for basic FPGA development, the standard prescribes a similar process, a similar development model as for software, as you can see it here. And the next slide, we will see that this applies also to techniques and measures to avoid faults, to avoid introducing faults. There's a similar system, as you might know it from part 3 on software. Depending on what safety integrity level you need to achieve, the more stringent, the more rigorous the methods and techniques you need to apply. I won't go into detail here, just to provide you a visual.
Okay. Now, this is the last of our 5 changes to cover today. And Thomas, can you share with us the main takeaways due to an increased focus on EMC?
Yes. Again, it's not really an enhancement, but again, just if you want an increased focus. Because, again, already the first edition was aware of the fact that electromagnetic phenomena, they are a main common cause, a main reason for common cause failures. They can attack, they can damage both channels at the same time. And the standard recognized that, well, the higher the SIL, the more immunity you should have, but it also recognized that it is difficult to determine the probability. So you cannot really take that into your quantification and your PFH calculation. So there's no guarantee that you reach a higher safe integrity level by increasing electromagnetic immunity, but you do get an increased confidence. But other than that, I think the standard was not very explicit regarding increased immunity requirements. And this has changed. This has basically changed because the advent of new standards that really are dedicated to this topic, functional safety and EMC. These are referenced normatively, so you no longer really can avoid looking into higher immunity. This is something that has been sometimes neglected with the old version, but now there's no excuse anymore. The first standard, or it's still technical specification, is in fact not only about EMC tests. I think it's primarily about appropriate design. The basic message of that standard is, well, that you cannot test yourself out of EMC problems. You need to do a good design. Compares it a bit to software. You cannot completely prove 100% bug-freeness by simply testing. You need to do a good and formal design. And it has a similar approach to EMC, and it suggests quite a number of good practices that you need to fulfill in order to have good EMC design. It does also recommend tests against higher levels and even against very high levels with a very low probability. Yet the other standard, it is a standard, and this is really more, I think, a test standard if you really want to put these two standards in two different boxes. So it defines a test plan, puts requirements on the test plan, but the configuration of the UT equipment under test must select the most susceptible configurations and installations and provide an argument for this. It also allows you maybe to not test certain I/O ports because they are similar in design to other ones. Again, you need to provide good argumentation for that. The operation conditions during tests, you need to identify worst case operation modes and document it. And but on the other hand, it also allows that you really use a test software. You don't necessarily have to use the final to be certified software, so you can do the tests really a bit early on in the development. But of course, certain things must be in place in this test software. You must be able, for example, to simulate these worst case operation modes. And then the performance criteria. Of course, the immunity levels, they are higher, but you could say the performance criteria is a bit relaxed, you could say. Of course, it's always fine if the safety function is not affected, but it is also allowed that temporary or even a permanent disturbance of the safety function as long as a safe reaction is assured, as long as you can always defined go into a fail-safe state. And that can go as far as really leading to the destruction of components. If this happens in a predictable and defined way, if you reach a fail-safe state in a defined way, then that would be allowed too. The next slide, very quick, just provides a visual impression again from the contents of that standard about the increased immunity requirements as they are applied to industrial environments.
Well, I think that about wraps it up for our discussion of the 5 main changes to the standards. Now, Thomas, I know you wanted to just call everyone's attention to a few of the changes that were made that we haven't covered in detail, and I'll just go ahead and put that slide up and read through it for you. So as far as the further appreciated changes that we haven't covered, you see on your screen new phase system requirement specifications and the new deliverables and system safety requirements and system design requirements. Second one there, clear definition of safe and dangerous failures as related to SFF calculation, requirements for proven in use and pre-existing software, requirements for tool evaluation, and modernization of software development techniques and measures. And certainly if you have questions you want to learn more about that, you can we'll be putting up some information on how to contact our speakers today. I also want to say thank you, Thomas, for all the great information, and I think if we asked that poll question again about the familiarity with the standard, we'd get some very different answers. And I do want to take a moment to bring Kevin back to the virtual microphone, the virtual podium, to share with us a discussion on the value add of the changes to the supply chain, and also to provide some of the information on the UL certifications that are available. And Kevin, it seems to me that the changes to the standard impact more than just the manufacturers. Can you share with us some of the specifics on how these changes have impact throughout the supply chain?
Yes, absolutely. So what we'll do here is we'll take a quick abbreviated tour through the supply chain, and hopefully we can see clearly the value each participant in the chain adds and how that's going to benefit their customer. So the end user, of course, wants increased safety, and they also want to reap the benefits of the higher and the newer technology available to them. So we look at the next link in the chain. The system integrator now will have a higher confidence in the elements, especially the elements compliant and complete with a safety manual, also provide ease of implementation, also provide the technology that the end user wants access to, and also at compliant EMC safety levels. So the subsystem level now provides the benefits using traceability, consistency, readily use the technology available, and again, the newer EMC levels. And for the elements then, traceability as well as compliance, and if applicable at that level, the element could be a microcontroller. And I just want to point out, I think there may have been a typo previously where it said ACIS. That was a typo. It should be an ASIC, which, an application-specific IC. So to sum up, throughout the supply chain, the second edition now does provide many benefits to the supply chain. However, the question may be, how does the user know the device is certified to the second edition? And of course, the UL mark provides a verification that the UL has certified the product. In addition, it includes the addition and date of issue of the standard, so it is evidence that the certification is to the second edition. This gives the end user or system integrator or subsystem user instant proof the device meets the second edition, and that they can reap the benefits of the second edition.
All right, well, thank you very much, Kevin. And I know we are getting toward the top of the hour, so I wanted to take a moment to put out the second of our polls today. So everyone coming up on your screen, if you would please vote. And the question is, which of the changes discussed today appears to be the biggest challenge? Okay, and it looks like it comes out with 36%. Looks like the high score there on increased focus on traceability, and 20% concepts of elements and compliant items, 17% redundant channels in a single integrated circuit, 4% field programmable gate arrays, and 23% increased focus on EMC. So thank you very much for that input. It's very insightful. Now, if you would like to get additional information, certainly can download UL's white paper as noted on the screen, www.ul.com/functional safety. Also, if you'd like to request a quote from the UL functional safety mark, you can contact Kevin Conley, and his number is listed there on the screen. Will also be listed on the next screen as well. We are getting toward the top of the hour, and I want to take a moment to start answering some of the great questions that are coming in from all of you folks. So with that, I'm going to ask Thomas to come back to the virtual podium, and Kevin as well. If you have questions, certainly can send them in to us. Just locate the control panel there and type your questions in, send them over, and we'll get to them, to as many of them as we can. So I'll start with the first question that we have here, and this one is directed to you, Thomas, and that's, does traceability only apply in development, or does it concern the complete supply chain?
Well, I think traceability as it is defined or explicitly required in the standard pretty much is focused on the development part. But it includes traceability to hardware components. So in fact, it only really makes sense if you extend that traceability to your supply chain, in that case, well, for example, to the purchasing department to make sure they buy the right components from the right manufacturer and they do the right controls and tests for all new components that come into the factory. So yes, traceability ideally will not only be limited to the documents, but it is really something that is implemented in the complete supply chain.
Okay, well, thank you very much. And this question directed to you, Kevin. Our products include FPGAs and need to fulfill PL as of ISO 13849, but ASIC or FPGA development is not addressed by ISO 13849. Is it possible to claim PL conformance?
ISO 13849 does not address FPGA development in the way 61508 second version does. Not sure if it ever will or should, as ISO 13849 is primarily a system integration related standard rather than a component manufacturer standard, but it certainly is possible to claim PL conformance for a safety system that contains FPGAs by applying the PL SIL mapping given in ISO 13849 and then applying the relevant fault avoidance measures in Annex F of 61508-2.
Okay, thank you very much. And this question coming in for you, Thomas, from James, and that is, has UL adopted IEC 61508?
Adopted? I don't think you can say it has adopted it. Not sure what is meant by adopted, but clearly it is an international standard, and UL provides certification and the UL mark in accordance with that standard.
Here's one more. Where does EN 62061 fit in? And any changes on this?
I think that's a good question, because what I would say is that many of the changes in IEC 61508 second editions, I think they're pretty much based on 6.2 or 6.1, for example, the element concept. I think this is something that really comes from 6.2 or 6.1. But really, IEC 62 or 6.1 really is, of course, a sector-specific derivative of IEC 61508, and there's a high degree of compatibility. Of course, I think IEC 62 or 6.1 at some point needs to be going through a maintenance cycle and needs to be adapted to the new version of IEC 61508.
Okay, thank you very much. And this one for Kevin. Does UL have the test facilities to do the EMC testing required at the levels required?
Yes, UL has test facilities throughout the U.S. and arrangements or test facilities globally to do all the required EMC test levels.
Okay, perfect. Thank you. I've got one more in here for you, Thomas. And does this standard have a direct application to medical equipment software development?
Well, IEC 61508 is really a basic safety publication, and it is globally recognized as representing state-of-the-art if you really have safety functions that are implemented using programmable electronics. And I think it is referred to by medical standards too. Medical standards derive requirements from it. I think even the FDA refers to it. So yes, IEC 61508 really can be used for medical application, for medical equipment, in particular also in connection with the 61010 standard. It's very often used in medical area, and this one, in its latest version, really directly references IEC 61508.
Okay, perfect. Thank you. And I've got a question here for you, Kevin. This one, does IEC 61508 relate to UL 508 standard?
Well, there is no correlation 61508 to the UL 508, but what we do for products that have a safety application, 61508 can be an additional investigation to a UL 508 product. So, maybe a solid-state motor controller or a PLC, which is still done to 508, I believe, that can be a normal product or a basic product, or it can also be investigated to 61508 and get the UL functional safety marks.
Okay, well, thank you very much. I've got a question here for you, Thomas, and that is, how does UL contend with reviewing highly complex systems that entails FPGA designs, design tool chains, microcontroller layouts, etc.?
Well, this question is basically about the essence of functional safety. This is the reason why we have a standard like IEC 61508, and really following the requirements, particularly the one we heard about today, traceability. That is, of course, a big help in really being able to manage that complexity and being able to understand the complexity and being able to focus on what is really relevant to look at in these complex systems. So when UL does a review and when UL does an evaluation, of course we will do a thorough job, but we will also require, also because it's written in the standard, that the manufacturer has good process in place, good documentation, formalized documentation, and traceability. This allows us to focus our evaluation effort, and this allows us to establish confidence in that really the overall system fulfills the safety requirements.
Okay, well, thank you very much, Thomas. I've got one more for you here. Increase in EMC levels are on AC power systems, or are they also applicable to DC input power systems?
Well, the increase, I think that's a bit, that's probably a repeat of the question before, but I understand it better now.
Yes, it is.
I think generally there are increased EMC requirements on all ports, on all interfaces, and that applies also to the mains input and will apply in any case. So if DC input or AC input really directly connects to the safety-related system, then you need to consider this too in your safety-related EMC test, and you will have to consider increased levels.
Okay, perfect. And this one for you, Kevin. And the question is, will UL mark the entire piece of equipment or only the individual components?
The UL mark typically applies mostly to the components at this point. If there is a need for a machine or an entire system, we can certainly provide a mark for that and a mark and a certificate to define what is included under that functional safety mark if that's necessary.
Okay. Let's see here. I have a question for Thomas. What do I do with an existing product that is already compliant and I want to bring it up to date to the new requirements?
Okay, well, that's an obvious question. Well, what I said in the start is I think that the fundamental principles of IEC 61508 have not changed. What really has changed is an increased focus on some things that have been loosely and vaguely defined. And well, an obvious problem could be that if you really have neglected the increased EMC requirements, so that could be a problem. So you would definitely have to test against at the higher levels. Another aspect could be the safe failure fraction value, because there are more stringent requirements how to calculate the safe failure fraction, or at least to the data that you can use to calculate a safe failure fraction. There's a clear definition of what is a safe failure and what is a dangerous failure, and that could be, so if you somehow, I would say, abused of that loose end in the first edition, then it could be that if it comes to an extreme, that you would have to go down in the claimed safety integrity level. But I think other than that, and in general, I don't think there are any backward compatibility problems.
Okay, well, thank you. And I've got an attendee who's just put in a question notifying that Kevin Conley's phone number is missing a digit. Kevin, could you give us your complete phone number?
Yes, I apologize. I didn't notice that typo. My phone number is 631-546-2691.
Okay, perfect. So just a 1 missing there on the end.
Yeah.
Okay, very good. All right, and looks like we're coming up on the top of the hour. I'm going to go ahead and make this our last question. And this one for Thomas. Which product types are required to comply to IEC 61508? Are there any best practices to follow when not required to formally comply?
Yes. Well, formally, it's difficult to really say what one means formally applies. I think what is a fact is that IEC 61508 is considered state-of-the-art for functional safety of programmable electronics. So if you're building products and you find out part of your safety depends on a computer, depends on software, then really in order to make things right, in order to, well, if you should come to an accident and so on, well, if you can claim that you have used state-of-the-art, then you can do this by demonstrating that you have followed IEC 61508. So IEC 61508 should be used whenever you identify that there are safety functions, safety-related safety aspects that depend on programmable electronics. Now, if you look at the functional safety marks that UL is offering, so these functional safety marks, they will not be applicable to an end product. They will not be applicable to a car or to a washing machine. But they will only be applicable to a control system that is inside the car or inside the washing machine that makes sure certain hazards, certain bad things cannot occur.
All right. Well, thank you very much, both Thomas and Kevin. And it looks like we're just pushing up on to the top of the hour. So I wanted to take a moment to thank each of you for joining us today. And I hope that you found today's webinar of value. Additionally, for any questions that we couldn't answer on air, we'll certainly have a UL subject matter expert reply to your questions. A special thanks to our speakers, Kevin and Thomas, and to our sponsor, UL. Also to Patty Van Hooser, who's working behind the scenes on the logistics. And again, as your moderator, this is Lori Dearman saying thank you and have a great rest of the week. And goodbye for now.